Good evening, everyone. Uh, on this very historic day, we are welcoming Bhaiya, our alumnus from BSMS Department of Physics in NIT Agartala. Sarwar Bhaiya, was one among us. He graduated from this very institute, and after clearing competitive exams, he has joined the Indian Institute of Space Science and Technology at Thiruvananthapuram, popularly known as IIST. IIST is the place where ISRO recruits or probably basically trains its engineers and scientists to contribute to its research and development and all the missions. Following his passions, Sarwar Bhaiya pursued and enrolled in a PhD program in Europe, particularly in the Max Planck Institute for Radio Astronomy, where he is actively researching on star formation, and his talk today will be revolving around star formation in the Milky Way. So with that address, I will also just mention some of the highlights of today, and on this momentous occasion of how we are arranging this talk today. So with Chandrayaan 3 succeeding in its soft landing, India has become the first country, to perform or attempt a successful landing, a soft landing procedure in the south lunar surface. India has also become the first country to operate a rover in the lunar south pole. It has become the fourth country to make a controlled descent onto the lunar surface. And in the 21st century, it is the only second country after China to reach the lunar surface. So four very historic facts which happened in front of all of us today in the evening. And with that, I would like Rick to introduce our club to Sarwar Bhaiya and the audience present here. So, Rick, you can proceed.
Am I audible and visible?
Right, right, sure.
Yes.
Yeah. So yes. This is Physicus, and this club was founded basically in 2020. While all the turmoil of the COVID has taken over the entire world at large, somewhere deep down, some of us physics enthusiasts in NIT Agartala, we wanted something to keep us busy and engaged because, we are people who are deeply passionate about the subject and wanted to explore the unexplored domains of it and utilize the entire COVID scenario to rather upskill ourselves and gain knowledge. That's when Physicus was born. Till now, multiple talk sessions from alumni, from various researchers. Uh, Overall, this is the 10th session that we're organizing, and that's a remarkable feat which we have reached. Also to mention, we have last year we had sent a successful team to represent our college at the National Science and NASA. Another great feat which we hit this summer was that we organized a hackathon, which we organized in entire northeastern India, and with a footfall of over 500. So overall, Physicus does a great job of the physics tasks in provide our students that are passionate as much knowledge regarding various domains and aspects of subject. Now, to hand over the proceedings to
Right. I think that was a very pretty welcome address, which focuses and highlights the motto of the club and the history of the club. With this, I would like Sarwar Bhaiya to begin his presentation so that we can be a witness to what he is doing in his research work. So, Sarwar Bhaiya, you can please proceed.
Okay. So thank you for inviting me to my talk, and I'm really excited to start this talk. And IIST took a very nice initiative, and I feel to continue and want to know more. It's great. And yeah, I also want to congratulate everybody for this beautiful Chandrayaan 3 landing, successful landing. Can you see my screen and my mouse cursor?
Right, right, we can see.
Okay, yeah, okay. Okay, so today I will talk about what I'm doing past 2 years as a PhD candidate. I'm working on basically on high mass star formation. So my topic of the presentation is galactic HII region in the GLOSTAR survey, and by hopefully by end of this talk, I will. I think everybody will know all these terms which I put in this title of the slide. Yeah, and I'm working under Professor Carl Menten. He is the director of the submillimeter group in Max Planck Institute for Radio Astronomy. Yeah, so for my talk, I will first give a brief introduction to many things like radio astronomy, then high mass stars, what are S2 regions, and the emission processes for S2 region. Then I will briefly talk about motivation, like what I am doing and what we would like to, as a science community, like to do with this knowledge of high mass stars and all. And then I will talk about this very nice project, the GLOSTAR project, which I am a part of. And then I will, in like few slides, I will just tell what I did.
Right,
So, starting with this, so radio astronomy is basically study of radio signal from the extraterrestrial objects, and yeah. So in this figure, we can see the atmospheric opacity. So this atmosphere is almost transparent at the optical wavelength and radio wavelength, and the window at the radio wavelength is very large. So because it's large, so we can study more and more astronomical phenomena with radio wavelength in compared to any others. And for the higher frequency radio, we can also do the science, but for that we have to go to higher site like mountains and something. But yeah, so that's why radio astronomy is very important, because it's covered a very vast range of sciences which we can do it, from the low energy physics to high energy physics, from plasma to pulsars, black hole images. You guys have must have known about that. Those are taken with the radio astronomy. So yeah, so radio astronomy is a very powerful and important tool to study the our universe. And another advantage of radio astronomy is like it won't get interfered by atmosphere. So basically, when you are doing infrared or optical observation, so you have to take care of the atmosphere, because of the cloud water vapor in the atmosphere can interfere with the signals, and you won't get a good result. Another point is like optical you can do only night, but with the radio these are not the cases. You can do it daytime and even anytime, even with the clouds, without the clouds, it's fine until you are doing low frequency radio wave. But if you are doing high frequency, then you have to be little bit careful about the water vapor in the atmosphere. And human interference is a very big problem in astronomy. But yeah, we are trying to solve it, and we are achieved very good in that. So yeah, so for to do a radio astronomy, we need radio telescope, and radio telescope can be, it's a metallic disc. So because the wavelength of the light is quite large, so we don't care much about the accuracy of the disc, because it won't be uh, scattered by the inaccuracy on the disc. So making disc is a it's not super easy, but yeah, it's a comparatively easy job. But the problem arises with the resolution. So mm, you guys must have known the like telescope resolution is inversely proportional to the size of disk. So if we have to make a very high resolution telescope, we need a very large disk. And then the problem arises, because when you make a very large disk, first of all, making a large disk is difficult. And the second point, you have to move the telescope. So all this creates a very challenging thing, like engineering challenge to create. So but still, like we have able to create 100-meter telescope, which is in Germany, and then another 100-meter telescope in Greenbank. Recently, China made 500-meter single disk telescope, but it's not a steerable telescope. It's yeah, it's mounted on the mountain, so you can't steer it. But still, it's a 5-meter telescope. So yeah, so when we talk about like checking, seeing the image of black hole and all, we need very high resolution, very high. So here I have show the example of for 1 arc second at the 1 centimeter of wavelength, we need a disk size of 2 kilometer, which is impossible. We can't make like that. And and when I talk about black hole images, the resolution of that image was, I think, 2 micro arc second. So yeah, then the size of the dish should be like equal to the radius of the Earth. Nobody can. But to solve this problem, we have done something like interferometer. What we do is we collect, like we install different small size antenna, and we collect data from all of them simultaneously and interfere their signal, just like interference you guys have studied in optics. So here in this figure, let's see, like there is a two small antenna, and they are separated by a distance of s. So I will now from onward I will call it as a baseline.
Right.
So they have a baseline of s, and so if we take, like for interferometry, the signal will look like interference patterns which we are familiar with, and if you keep on increasing this s, this pattern will become more narrow and narrower. So you are increasing the resolution. The problem here is you can see patterns. So you have to remove this size pattern, else you won't be able to do anything. So to do that, what we do, we add more than one antenna. So as soon as you start adding more antenna, like two antenna, 5, 10, 100 antenna, this pattern will become more well defined. So the central peak will go very high and the side will go very low, and you keep on integrating the signals, and the signal will start looking good. So yeah, so with this you can achieve a very high resolution uh, images. So for EHT, the longest baseline is around 1,000 kilometers. So they have telescopes in radio telescope in USA. Then there's a radio telescope in South Pole, in Chile. So they have connected all of them. So what they do, they collect the data from these telescopes separately. They bring at the same point, same place, and process the data. Basically, they correlate this data, and then they get the final signal from it. So yeah, it's for science, it's good, but it's required a very large computational power, because you are correlating very large amount of data. So so most of nowadays, like in radio astronomy, if you don't, if you need a good resolution, we go for interferometer. But in some cases, even single disk can be still used. For example, if you want to see the diffuse emission in the galaxy, so like, which means you don't need high resolution. So you won't go for very large single disk antenna, but you observe it, and then it will give a low resolution diffuse emission image. So yeah, there are like some famous example of interferometry. So there's a one in VLA. So the longest baseline for VLA is 36 kilometers. So again, like last time for single disk we were talking about 100 meter. Now we have at 36 kilometer. And India also has a very beautiful telescope, GMRT, and that also has a interferometric telescope only, and it has a baseline of 25 kilometer. And recently they constructed another interferometer in South Africa, Meerkat. It's had 8 kilometer, and there are many more. So it's not only this. There is Alma. There are So these three I put as example because I work with these three mostly. So in my master, I work with GMRT, and right now I'm doing with VLA and Meerkat. Yeah. So now we have. So this interferometry thing, I told it like very briefly. If somebody wants to know in detail, you guys can contact me anytime. I will tell you in detail. Yeah. So another thing is like. So we want to study galaxy, for example, like, and then there's many options, right? Like you can do it in X-ray, you can do in visible ray, you can do in radio way. So how somebody will select which I want to do? Like, why will I go for radio, why will I go for optic? So this depend on the science you want to do. For example, if I want to see the how the neutral hydrogen is located in our galaxy, so I will take 1.4 gigahertz, which is radio. So this map show the distribution of neutral hydrogen in the Milky Way plane. Similarly, if you want to study molecule, you go for little higher frequency, but still radio. Then infrared, you go to study the star formation and all those things. And yeah, James Webb is infrared telescope. So yeah, it's very important. Then there's then optics. The problem with the optics is it's highly obstacled by the dust. So galaxy is filled with the radio dust clumps, molecular clumps, dust clumps, and radio light. Sorry, optics light can pass through them. So that's why in this image you see this uh,
Just.
black patches in the galactic plane. These are the location of the dense dust clump where optical light can pass through. Contrary to this, if you see the radio image, you will see where optical is dark, radio is bright. So that's how you select. So for example, if I want to study the star formation, so star forms inside the dust, dense dust clump. So I won't go for optical because I know I won't be able to study it well. I won't be get signal. On the other hand, if I use the radio, yeah, because radio wavelength are very long, so they can easily penetrate dense dust clump and all. And for the high energy physics, gamma ray, X-ray can be used. But yeah, so yeah, so the basically is you can use different type of wavelength to study the same thing, and everything will give you something new. So that's why it's multi messenger Milky Way, because like you can do multi wavelength. Now in recent year, even gravitational wave is also added. So in future, we will do more science with the gravitational wave also. So yeah, this is an image of something in radio. I want you guys to guess it. Maybe think about it. I will ask later. So I will give you a hint. It's a solar system object, and let's see. Yeah. So now we know like we know radio astronomy, why we do, how we do it. We know when to use radio astronomy, when to use optical, all those things. Now, as I told, I want to study the star formation. I want to know how stars form. So for that, as I told, selecting optical is not a good idea. Infrared and radio is a great idea. So now I will tell like briefly about star formation, how we select a star, why stars, why anybody wants to study star. So it's a beautiful image of sun, and sun is a very regular star in Milky Way. It's nothing special about sun other than it's closest to us, and all the life is provided by it. So other than that, in terms of other stars, it's just a regular star. However, there are billions of stars in our Milky Way itself, and there are billions of galaxy. But in our Milky Way itself, billions of stars, and not all the you don't expect all the stars to be same as the sun, right? So different star have different. Even with naked eye, if you see sky, you see some star look little bit red, some star look little bit blue. So why is this? So initial days, scientists thought about that and they think like we should classify star, but it was not a easy job. First of all, you need a very powerful telescope to do that. Other than, and then that time we had only optical telescopes which didn't have that much power resolution. So it took many decades for scientists to figure out how to classify. But late, sorry, but later they what they did, they start taking spectra of stars. So you take a star, you pass through a spectrometer, like for example basic, if I say, like pass through a prism. So for our sun, if you pass it, it will say rainbow and all. But if you increase the resolution of a spectrometer, then you will start seeing for some particular type of star, there's some lines are missing. So like for example, if you take type A, just consider some type of star type A, you see this hydrogen beta line is missing, some line is like more broadly missing or something, and in some of the cases there are many line missing. So they started to think about, like, yeah, we can do classification based on that. So the first classification of different type of star come with the hydrogen or some line distribution. But not only that, we can also do it with the strength of the line. So when electrons in an atom jump from higher energy level to lower energy, they emit light. Yeah,
Right.
but that population jumping from up and down is highly sensitive to the temperature. So if you change the temperature a little bit in terms of astronomical terms, when I'm talking little too little. So if we change it slightly, the strength of the line change. So they started checking the strength of these lines, and based on that, they decided, okay, there can be a star which has like very high temperature of 5,000 Kelvin. There a star which has like 3,000 of Kelvin temperature. Our sun has around 5,500. Yeah, yeah, between 5,600 something. Yeah, so this is another classification. And then another they did, like, it's a Herschel diagram. So what you do, you draw the position of stars on a luminosity versus mm, their spectral type or their temperature. So y-axis luminosity, x-axis spect sorry, surface temperature, and you start seeing this, all these stars follow a very nice pattern. So like most of the stars is following this pattern, whereas some of the stars is sitting somewhere. Still, it's not random, but not in the main star. So they figure out this long pattern is associated with their mains life. So star evolved from very like hot core to then they reach main sequence life when they start burning their hydrogen. Slowly this hydrogen got over, they start burning helium, and they expand, they went on supernova. Yeah, so like different stages of their life. So this purple line show the main sequence, which is the sequence most of the time starts it. So sun is right now is in main sequence. As sun age, it will move up and then it will go down. So it reach the supernova stage, late stage, and then it explosion will happen, and then it will create a white dwarf or something like that. So yeah, most of the stuff follow this pattern. So with this, we know that like there are many stars, but not all stars are same. So you can classify these stars based on their temperature or something. So from now onward, when I say the some high mass star, so what I mean that those stars have very high mass and their temperature is very high. So I will be mostly talking about 3000 Kelvin or 5000 Kelvin stars. So these are, yeah, these are very energetic stars, and yeah, later we will talk about more. So our sun is a G2 type star, so it's like 9000 Kelvin, sorry, 5900 Kelvin in the main sequence star. So now we know there are different type of star, and we know that how they evolve. So for example, let's take an example of sun-like star. So first it will form in a dust clump, a molecular clump. Then it reach a protostellar stage. Protostellar stage where the sun is accreting material from all sides because of their gravity. As soon as their mass keep on increasing, their gravitational pressure increase and star start burning hydrogen. So nuclear fusion started, and then it become a main sequence star, just like sun. And that main sequence stay for very long time, billions of years. Then slowly the fuel will got over, then they start burning higher element like helium, carbon. After some time, even that will over. So the balance between outer radiation and gravitational will stop, and they went on supernova explosion, and they will create a white dwarf. So this is sun-like star, which is like they don't have mass, very high mass. So we know very pretty about these stars because most of our neighbors star are small stars only. So we can observe them, we can study them, and since their age is very long, so you can find many sun-like star in the sky, and you can do study. However, in case of massive stars, which is like 10 times or 8 to 100 times massive than sun, they also go through these things, but they do it very fast. So they first form protostar, then they start burning things, and because their mass is so high, so gravitational pressure is so high, they burn everything very fast. That's why they have very high temperature. And said in within millions, like 10 to the power 6 here. For sun we talk like billions of year. Here in within millions year, they finish their fuel, they will go in massive supernova explosion, and they create neutron star and black holes. So yeah, so this massive star is not very well understood, and the reason is because they live for very short period of time. So it's like in terms of astronomy, million year is nothing, whereas for low mass star they live for like billions of years. So you can still have large sample size to study them. So yeah, so as I told, like why we want to study high mass stars. So first of all, for low mass stars we already know about them pretty well. It's still not completely known, but we know because of all the neighboring stars we have, we know pretty well about them. But for high mass stars, we don't know many things. And why we want to study them? Because although they are in small in number, they live for very short time, but they do many things to the galaxy because they provide very high energy radiation. They go on supernova explosion. So they control the energetics of the galaxy. Another thing is like when they form, they eject outflow. In the second figure you can see this star is forming, and there is a two outflow is coming out, and this outflow happen to balance the angular momentum, because along the disk you are accreting material and it's rotating. So to balance the angular momentum, it start ejecting material in both directions, and these are a very high energy particle. They move very fast, and yeah, so it's like very energetic. So they control energetic. They help in evolving their interstellar medium, because this supernova explosion they release huge amount of high metal, and then highly ionized gas in the medium. So this will keep on affecting the next generation stars and all. They can define the structure of galaxy also, because they form in only in the dense clump. So if you know where are massive stars are forming, so based on that you can get a picture of how our galaxy look, because we are lying on the galactic plane, so we can't see from up how our galaxy are actually, whether it has two spiral arm or three spiral arm, whether it has galactic bulge or not. So it's difficult to do all this study, but these is, if you know this high mass formation stars location, you can do. So this is a very old paper, so now we have done very much better than this. But yeah, so here you can see, so they have studied the different star forming site, and based on they calculated the distance, and based on they give a basic idea how our galaxy look from upside down. So yeah, so they are useful to study the galactic structure also. Another thing is metallicity, as I told, like because they burn so much fuel and very fast, so they produce very high atomic number elements. So yeah, so and they live for very short lifetime, so they it's a high and they surrounding, and they change the metallicity of the galaxy, their host galaxy. And the change in the metallicity also play a very important role, because that's defined how efficiently star will form, all those things. But that out of the scope of this talk. But yeah, so they control the metallicity also. Another thing, they can trigger a new star formation in their neighbor. So here is a picture. So this dash oval shape, it's a location of a star which ejecting material in all around, and they have found many new star forming around this circle. So uh, so they pointed out this high mass star is spreading new photon energy around them. So it's also a very important point. Like, which means if you see a high mass star, you should see more and more star forming in around them, or they can destroy also. But that's not. So basically, they have played very important role in the formation of galaxy, chemistry of the galaxy, structure of the galaxy, everything. That's why it's important to study them. But studying them is not very straightforward. It's very difficult because first of all, as I already told, they have short life, so you don't get a very large sample of these type of stars. Another thing is they are in small in number, so in compared to normal uh, low mass stars, the high mass star is very less, and their distance is also very large, which is that's why it's really difficult. But yeah, so their distance is very large, so we need a very powerful then resolution telescope to study these things. Main biggest problem is they are embedded in deep inside dust clump, as I'm pointing again. So you can't just take a telescope and say, oh, I want to look that star. It won't be happen because they are small, they are at very far distance, they are surrounded by dust and molecules, everything. So for example, this is Bernard 68 star forming region. So in optical you see this dark patch, but if you see the same thing infrared, you will see actually inside this dark patch many stars are forming. Yeah, so if even if you go in radio, you will start seeing more things. So that's why they form in very dense environment, and studying them it's not straightforward. Because and then we also didn't know very well how the magnetic field play the role in the star formation. We didn't know what decide how massive will a star form. Because if a star is accreting material, what is stopping it to accrete? It can keep on accreting and become thousand solar mass or whatever it can do. But for some reason, at some time, it stops accreting material. There are some theory about that, but it's not well tested theory. So we are doing those testing and all. So yeah, so formation of high mass is still not very clear, and sorry, and it's still not clear. And as I told, directly observing them, it's not a straightforward thing. So what we do, so we find a uh, tracer. So H2 regions are a tracer of high mass stars. How they are tracer, I will tell. So when a high mass star forms, they emit huge amount of UV photons. UV photons is like high energy photon, which is like 3.9 electron volt higher energy. So which means they can ionize hydrogen very easily. Why they emit UV photon? Because I told like, so basically stars follow black body curve, and if you keep on increasing the temperature of black body, the more and more higher energy photons you will get. So these high mass have the energy of 50,000, 36,000. So they produce huge amount of UV photon. These UV photon ionize hydrogen around them. So as in shown in this picture, there is a massive star. It ionize hydrogen around them, and it produce H2 region. So H2 region basically a zone of ionized hydrogen around a massive stars. These H2 region expand because of pressure difference between inside and the outer molecular cloud. They form, yeah. So there's a different structure of the H2 region. But for the simple picture, H2 region is ionized gas around a massive star, and they can evolve with time. So if I see a asteroid in Milky Way, and if I see its size is very small, and its density of this asteroid, sorry, density of H2 is very high, then I will know this might be a young H2, which means like recently formed, which means the star inside that H2 is very young. If I see a very large H2 with very low density, then I know this is not a new H2, it's a late type H2, and the star uh, which was behind formation of this H2, it's now evolved. So yeah, so we use H2 region to trace the different stage of massive stars. So that's why asteroids are the great tracer of early phase of massive star as well as later phase of. But we are interested in early phase, yeah, right, because we want to know how massive star forms. So they are very great tracer of uh, greatest of early phase of star formation. Now, how you trace asteroids with the radio telescope? So, asteroids you can by thermal radio emission you can detect them. You can detect them by submillimeter emission, their mid infrared emission, and radio recombination line. The second and third part I won't talk here. So the I will only talk about the thermal radio continuum emission and radio recombination line. This thermal radio continuum is also known as free emission or thermal emission or thermal bremsstrahlung. So what happens? So in the ionized zone, you know this electrostatic force is more powerful than the gravitational force. So when an electron pass through a photon, it accelerates. This acceleration causes in emission of the photons. So these photons are nothing but the free emission. So from the S2 regions, we receive a huge amount of free emission, these types of photons, because it's full of ionized particles, electrons, protons, and they are moving very fast. So they keep on emitting. And these emission generally happens in radio range. So like from zero point 0.1 gigahertz to 10 gigahertz. So that's why it's with radio we can easily trace asteroids very nicely, and it's a very nice tool to do that. And they are very bright also. In another thing is, so as you guys know, when electron jump from higher to lower energy level, they emit photons, right? So for the first uh, uh, Balmer series, it is like 3.9 sorry, 3.9 electron volt of energy they release. But if an electron jump from very high energy level, let's say, and quantum principal number of n equals to 100, then the difference between the energy level is very low, and the photon which you get will be a radio photon. And since radio can go through the dust or like dense region, so we can trace this recombination line. We won't be able to trace higher recombination line which have high frequency, but low frequency recombination line we can easily do that. So here's an example of an H2 region. It's I named it like G49. It's a name based on the location. So it has a asteroid, but as you can see, it's not a spherical asteroid. It has some other shape on it, like donut-like shape. Like one region is very bright, the emission is very low, and in the mid-infrared also, the emission look very similar to radio. So the first figure is free emission, the second one is infrared, and the third one is recombination line. So if you see a region which has recombination line structure like this, the characteristic mid-infrared emission, then you know it's an S2 region. So that's why using these three tools, you can detect, identify as many S2 regions you can do if you have enough powerful telescope and all this. Yeah, so hopefully I've given you the basic idea of things. So based on this knowledge, so what we want to do? So we want to check how where high mass star is forming, how they are forming. So we search for the H2 regions in our Milky Way. Then we study the physical properties of H2 regions, like their temperature, their velocity, how the gas is moving, is gas is colliding with the surrounding material and all. And the third is we want to know their distribution in the galaxy so that we can predict the structure of the galaxy better, and we want to know the distance. Okay. Obtaining distance is also not a very straightforward process, but for now, I just take it like we know distance. We can do many other things with this, but I won't talk about it right now. So let's see the first three only. So to do that, in Max Planck Institute of Radio Astronomy, they have conducted a large galactic plane survey. So they use the Effelsberg single disk telescope, VLA interferometry telescope. They scan a large portion of the sky, which is like from 358 degree to 60 degree in Cygnus X region. So yeah, and uh, they observe continuum emission, they observe recombination line, and many other molecule emission also. So which I won't talk about it, but yes, so we observe recombination and continuum. So since I have the data for recombination line, I have the continuum. So using that, I can look for the this S2 regions in the galaxy, and this is what I did. Sorry, yeah, this is what I did. So using the recombination line data, I recently cataloged the galactic S2 regions. So we have found around 244 S2 regions. Out of these, like nine S2 regions were new, like it was not discovered before. And this figure show the distribution of these asteroids along the galactic longitude. So this zero is towards the galactic center. As you move towards the left, that angle is changing. So we have detected many towards the galactic center. Yeah. So these are the different star forming region, and similarly the distribution of latitude above or below the galactic plane. So you can see the most of them is like within -1 to 0.5 degree. So this plot itself tell that our galaxy is not like spherical or something, but it's a plane. Because if you're looking and the angle is not varying too much, so you know the most of the thing is that within this small region only. So it's a hint that the galaxy is not spherical but plane. Yeah, so then we calculated the distance of these S2 regions, then we overlaid on the galactic image, we correlate with the models, and we found this all the galactics models, which like galactic had like different arms, like 3 kiloparsec arm. There are different arms. Those are in detail you can study later. But yeah, so there are different models to explain the structure of galaxy, and when we found the distance, we correlate with them, and it seems like those models are correct because where they are saying you should expect a star formation, we are also seeing asteroids along those arms only. It's not like randomly distributed here and there. And this is the another example of the same figure, and this also follow the models very well.
Right.
Yeah, so explaining this physical property is quite difficult, but I will quickly tell you for the one reason. So we have detected recombination line toward this reason, and for each pixel we get recombination line. So from recombination line you can calculate the velocity of the source. So in this velocity and line width, so line width also very important factor. If your line is very broad, which means the dynamic motion of the source is very wide, like there's a very high dynamic motion. If the line width is not that broad, which means source has like settled down, it's not. So you can see in this particular source you can see different band of line width. So for here upper side you see very high line width, which means like there's lots of dynamic motion is going on the other side there is not less. So based on this we concluded there might be two different type of cloud, which has like low velocity, sorry, low line width and high line width, and they are colliding with each other. This is why we are seeing this gradient of line width. Similarly, we calculated electron temperature. So because the source has ionized electrons, right? So you can calculate their thermal temperature. And for S2 region, it's generally around 1000, and we also saw it's like very uniform electron temperature of 6000 or something.
Right.
And for the emission we have like different type of emission. I talked about thermal emission, we also have non-thermal emission, so which are non-thermal emission generally produced by high charge particle going through magnetic field, and they produce non-thermal emission. So based on the spectra, their spectral index of the emission, you can guess whether it's a thermal or not. And when we did that for this particular source, we found that most of the emission is thermal because the spectral index was 2. Okay, this I'm saying like just maybe it will be difficult to understand now, but just take the point, like most of the emission from these regions are thermal as expected, like S2 region emit thermal sources and all. So yeah, it's just a basic example I gave for one sources, and we had done this for like 244 sources. So we cataloged all the sources, we calculated their property, and the paper is almost ready to publish. Yeah.
Right.
So yeah, so this is my talk, and hopefully you guys have learned something. And yeah, thank you.
Okay. Thank you, Bhaiya, for your wonderful talk. I think we got to know why we are probing the Milky Way using radio wavelength of light, not the
Mm.
optical one, and how the H2 regions are very helpful, as you told here in the gas dynamics. So,
Mm.
and even the star evolution and formation stages are also to be well understood by that. Okay, I think if anyone in the audience wants to answer this question, uh, is anyone waiting?
Okay, so I will tell.
Look, let
Is
me guess once. Is it Saturn? I'm not sure.
close,
Okay,
but not Saturn.
okay,
So this is Jupiter.
okay, okay.
So this is how Jupiter look in optical, and the image I showed is like in radio. And why is that? Because I told radio generally probe the ionized region. So
Mhm,
Jupiter's south pole has produced aurora of very high energy. So in Earth, aurora happen at the green light. In Jupiter, it happens in the uh, ultraviolet light, I guess.
mhm,
Yeah. So they produce high amount of ionized particles. That's why we are seeing this tumble-like structure.
mhm.
So this is the main Jupiter, and there are two poles.
Right.
Yeah. So see, that's why another. So that's why you do different type of different wavelength astronomy, because you just changing the wavelength, you might see completely different thing. Yeah, so that was my talk. Thank you for listening. If you guys have any question, I will
Yes,
happy to
sir.
answer. And if
Uh,
you guys are interested in something more about astronomy, here are some references which I can provide. Yeah,
Sure.
thank you.
Members of the audience, if you have any technical questions from Bhaiya's talk, you can ask right now, or else we will be moving on to the career journey conversation about how Bhaiya is, where he is right now. Okay. So, any technical questions from the talk? I think there are not anyone. There's no one asking such a question. So, okay, let us begin with this set. That is, like, how was your high school or childhood life was like? Because like people who get into sciences and research, they have a slightly different childhood or a slightly different school life. Okay. uh, or they are
Hmm.
slightly more curious. So what was it for you? Do you remember any fun incidents or some scientific
Yeah,
incidents to share?
yeah. So, so I studied in Kendra Vidyalaya in my whole life. So I was like more into sports than studies. I'm still in very into sports.
Okay.
So till I think seventh grade, I was not a good student.
Hmm.
I was just like average or below average only. But I remember one incident in eighth class. We had a new science teacher, and after unit test, he said like whoever got marks more than 35 out of 40, I will give that person a pen.
Hmm.
Okay, and for some reason I got 35. I just did,
Okay.
and I got 35, and then he didn't believe it. He said like, how is it possible? Like I was below average student, so he asked me questions in front of whole class from the paper, and I felt very bad about that. Like I'm that bad. Like he can't even believe that it's not even 40, it's 35. So I took it very seriously, and that teacher was good also because he was very good in teaching. So I become more close to him. Then I started studying more about science, and this was like I started studying for hours, but I started studying with more interest, especially science and mathematics.
Right.
And that teacher was also very good. So from there only, I I started leaning towards physics and mathematics. So and then it continues till 12. And other than that, it's like just normal life, having fun. I played a lot, just did normal thing. But that time onward, I know that I want to do something in physics only. So
Right.
I knew that what I wanted to do.
For sure. So after that, after completing your class 12th, you took the JE, which is in itself a challenge. The course load is heavy, and every aspirant who writes the JE exam has, obstacles which is very unique to him or her. So, what were those obstacles when you were writing the JE?
So at the first place, I never wanted to write JE because at that time I didn't know about this BSMS BTMT program. So
Hmm.
I told you like I wanted to do physics. So I wrote KVPS. I failed. I wrote. There are some more science exam which I failed like anything, but like my brothers and they said like you still write JE because if nothing then you should do engineering. I like okay, since nothing is happening I will do that.
Right.
And I also wrote ND exam because that time I really wanted to go in army also.
Okay.
So I remember my 12th board finished on 23rd of March,
Hmm.
and my NDA exam was on 7th of April, and J mains were 14. Yeah, something like that. So I studied for NDA. I studied very well, and my exam went very nice. So I was so happy, and I thought, okay, J mains also I will give. I took some crash course, and I did, and I gave J mains, and somehow I got qualified for advance. So I didn't plan for that, but it happened. And after J Mains, I went on home, like my village, and I spent 1 month there. And when I came back, I gave that advance. I realized like I should have prepared. It was very difficult. I didn't even expected that difficult. But my JE scores were luckily was good enough,
Hmm.
so I was able to apply for. So my home state that was Andhra Pradesh. So it's
Okay.
NIT Varangal.
Right.
So in counseling, I was able to get metallurgy in NIT Varangal. And I remember after this counseling, I was sitting outside and thinking what I will do in metallurgy. I didn't know anything about the metallurgy. So
Right.
I went inside in second round of counseling and I rejected that offer. And I, because when I was checking, I thought, oh, I will get NIT Rourkela easily in the physics. I didn't expect to get an IT Calicut, but I thought Rourkela is fine. I will do it. And then this was the first time this new counseling system happened or something, and their computer crashed, and I didn't got an IT Rourkela, and I thought like, oh shit, I did a maybe mistake, but then I got an IT Agartala for physics.
Okay.
And I thought, okay, I will take it. Like, so my brother, my friends, everybody told me like, you can take a break 1 year and prepare again. I said, no, I'm getting physics. Let's see what will happen. We will see. Just a minute.
Right.
Yeah, so I thought like I will do the physics, and in my mind it was there that ND exam went very well.
Hmm.
So I thought I had a backup. Okay, so I joined NIT Agartala first time when I came. Then only realized I was the first batch. Okay, that was a very big shock for me. And then yeah, that time was very interesting. The, like seniors, when senior asked to ask the introduction, I used to say BSMS. They didn't even know about BSMS. They said like, "What is this? Is there any such branch and all?" So I had to explain them what BSMS. Then they asked like, why you are doing physics in engineering college? What do you think you're too good in? All these things they had to do. You know
Right.
about this introduction and all those things. Yeah. So I went through this for 1 year. Like first year was my like I'm studying physics and doing this only. Like
Okay,
it
so
took
you
me
basically you were
like
explaining to the entire college who you are about BSMS physics, right?
yeah. Yeah, not only me, like whole my friends in the batch. Like in BSMS, there was only four people: me, Priyanka, Gri, Ajit, and Priyanshu. And in BTMS, there was like 6, 7 people. Yeah, that's all in this whole college, and we had to explain. And sometimes they got confused, like what is difference between BTMT, BSMS. All those things was going on.
Right, right,
But in October, I got a call letter from NDA. So like I got selected for the interview. I thought, okay, okay, I will go. So I went to Bangalore, gave the interview. I got rejected. In 2 days, I got rejected because yeah, I was not feeling well or something. So then I came back. I thought like, okay, so this is what I have, and I'm happy to. And I was never sad to study physics. I was not depressed like, oh, what will I do? My friend will get job and all. I had no problem such like that. I thought, okay, I will be happy to study physics. And so first year I studied a lot. I got a very nice number, and I studied a lot. But then I later realized like enjoying is also part of life, right? So
Okay.
after
You
that,
score a 10 CGP
yeah.
or something.
So yeah, in first semester, 9.2 I had,
Okay.
because English was there and I never studied. So I remember when I went to give the English oral, they take oral exam or something, right?
Right, right.
Yeah. So group discussion. The faculty there, he asked me, "Who are you? Why are you here?" Because he don't even remember me. I was part of this. So first time, so English I didn't get well marks, but like in physics and everything, my marks was very good. So because I studied very well. That I say,
Right.
and I was happy about that also. I met some nice seniors also, because they also told me, like, no, if you're doing what you like, then you should do, don't listen to other people, because there was very discouraging people also, right? You will find all kind of people, but you always select one which helps you, right? Not discourage you. So there are all type of people, but there were some seniors also. I made very good friends. So yeah, I had lots of fun, and then
Sure.
yeah, life goes on.
So when you first arrived at NIT Agartala, what was your like honest reaction to the campus and everything? Like, what was the raw reaction like? Just give us an idea about that.
Yeah. So when first of all, when I landed in the airport, and it took 1.5 hour, 2 hour to reach NIT Agartala. So I thought like we already left the city, we already left something else. Where are we going? It's very far, right? And then when I came to campus, I entered from the main entrance. Yeah, I that time I didn't like the campus that much, because that this new building was not even there. So
Okay.
there's like old gamma. I was like, oh, it seems like very old. And then I checked about NIT Agartala in their website of this, Wikipedia. It's like from 1965. I like, am I going to study in the college which they constructed in 1965? Because Tripura Engineering College, a regional college, was like that. Yeah, so first few days I was like, I don't know what's going on, whether I will be able to do it or not. But then I went to a hostel, met with the people, and there's like just, it's like later you just deal with your situation and keep on going.
Yeah,
Yeah.
sure, sure. Moving on, and then like you took up BSMS physics. This is true. So, like, what was the situation in your like family and society and relatives? Like, were they happy about you taking
Sorry, I
physics?
was not able to hear you properly.
Yeah. So
Can you
what
repeat?
I'm yeah. Can you hear me now?
Yeah.
Yeah. So you took up BS in physics, BSMS in physics, and in the society and family and relatives, there is a stigma associated with it that it does not pay well and stuff like that. So how
Yeah.
did you counter that stigma?
So in my case, yeah, there are some people like, my father was first of all not very happy with doing that. He was also asking the same thing, like, how much you will earn, how will you earn. And but my elder brother, he already did engineering, so he knew all this. So he supported me well, and he also convinced everybody like, you don't worry, he will do much better than the any regular engineer or something. Like life has so many options. So he, on behalf of me, he convinced many people, and I also try to convince many people. If they understand, it's fine. If then, who cares? So all I care about my family members and some and myself. So
Right,
I was convinced that what I'm doing good, and I will do it well. I convinced my father and my family members. That's all. After that, I didn't care. I,
right, right.
I didn't care at all
True.
about the society and all. In villages when I used to go, they used to ask us questions like, "What are you doing? What is this? Like, will you even earn any money and all? Why you are going so far if you don't get a job and all?" They have to use ask the question. I just used to say random thing and just move on. Like, I don't care.
Right,
Yeah.
right.
And in the words, just said like, after 4 years I will become a scientist. So when people hear scientist, they feel like, oh, something good only. So say it and move on.
Right,
So
right.
yeah.
So, college lectures, are so different from school classes or JE classes. So, when you what was your opinion about college lectures? Were you happy about it, or you felt sort of not so happy about or excited?
No, I was not happy about it at all.
Right.
There's no question in that. I can. After first year, I never went to class also.
Right.
So I was like just done. Like I thought like I'm not gaining any new knowledge. What they are teaching, a few of them was good. Okay, so I have to be diplomatic also. Few of the faculty was good,
Right.
and so but most of the them I didn't like that lecture at all.
Right.
Nothing. So after first year, second, third, fourth year, I never went to class. But I used to study because I like physics. So I knew what they are teaching. So like for example, quantum mechanics. So in quantum mechanics, for whole semester, for some reason, all we did is derive the hydrogen atomic structure equation, like Heisenberg. So
Yep.
this derivation went on for one semester, and okay, I thought it's good. Okay, we are learning, but 6 month thing, all you know is like how to derive it, and the same thing will come in exam, and that's all. But the question is not how to derive this equation. The question is how these equations are useful. What are you learning from it, right? Like uh, in 12th, I knew that like oh, hydrogen has a circular orbit. Then later it's p block, ns block. Then we when you study this quantum equation for hydrogen atom, then you will come to know okay why it's actually a like double dumbbell size or spherical size. So those are the important part, and that's what I was doing at my free time. I will being honest, I was not studying much, but yeah, in free time, whenever I get chance, I used to read all these things which interest me. And before exam, it was very easy to prepare for exam. Right, take a note, ask somebody, take a printout, read all the derivation, and you will score. So exam was a never problem for me. All I wanted to do is like I knew in my mind I should never lose interest in physics. It's okay if like I'm not having fun in my lectures. It's fine if I'm not scoring marks. That's fine. But I should not lose the interest. And to maintain this interest, you keep on reading something.
Right.
If even if you're not coursework, something. Just go to library, take a modern physics book, read that. If you find some documentary, study about that. So during my second third year, I used to take many astronomy book from my seniors or something. Although I was not understanding them, but still I'm liking it. So that's how you just maintain your interest, and you
Right.
should ha- have a clear idea in your mind what you want to do. So
Mm-hmm.
these two things I had. I always wanted to pursue in physics only, and I always have an interest in that. Yeah, and in physics also, astronomy came later, but overall physics, yes, I had that idea. So yeah, so for I was sad about lectures, but yeah, we just managed. All these friends we used to just bunk class and having fun and studying for the exam together. So that went well only, I guess.
The night before
Hmm.
exam, right? Okay.
Yeah, that's all you need.
Right.
For exam, that's all you need actually. And if you want to really study something, you take out some time, like not every day or not like 4 5 hours every day, but whenever you have time, whenever you feel like, okay, even if not time, whenever you feel like, you watch something, oh, I want to know a little bit about it. Just go take books, search internet, there's everything. So just maintain your interest. It's
Right.
good to have interest and maintain your focus. So
Right.
I think these two things play very good role for me.
Mm.
Although I was not doing well in study or all, but still I knew what I want to do.
Yeah.
Yeah.
So, especially in the senior or higher years, did you lose the interest and like sort of motivation? And what was your low point in your academic career in NIT Agartala? Did you witness some low point?
Yeah. I had low point many times actually, but like the one which I remember very well is during my fourth year. Yeah, when I reached fourth year, and so fourth year company started coming, people they start moving in their like career, they're preparing for that. And that time I used to think I have nothing. I didn't even know where I will apply after 4 years. I didn't even plan like whether I will stop BS or I will do MS also. So that time I felt like okay, this is not correct, and I felt very bad, like it was like a bad time. And I thought like I have to make some decision, and I have to make a solid decision. And I think that time only I decided I will do gate. I will get the gate that time only, and I started looking for what uh, after get what I will do. And so I selected some institutes. I was very picky about that. So I wanted to do astronomy. I wanted to do masters in astronomy. I don't wanted to start read physics again and do coursework, all those things.
Right.
So I found like ISC Bangalore, IST. So I knew that if I score a good marks, I will get there. And then there was TFR exam also. Yeah, and during that time I gave the TFR exam and I qualified that exam, but I got rejected in interview. So many rejection in ICTS. I went. I was so happy when I got call later from Indian International Center for Theoretical Science, Bangalore. I was so happy, like, and then I went there, and then I realized I'm not prepared for that, because I met with the other candidate. They are much well prepared. They know more than me, and I thought, okay, at least you qualify the exam. At least you got the experience to reach there. At least you got some experience how interview goes, especially this higher study interview. So overall, it was a nice moment. I was sad, but I got rejected. But
Right.
um, one part of my heart knew that I'm not going to got selected because I was not that much prepared. Yeah. So after that, I started preparing for GATE, not very regularly, but I was doing. And then for masters, oh sorry, bachelor's final project, you guys have to take 6 month project, right?
Mm-hmm.
So initially, I got the project in plasma physics,
Hmm.
and I thought, no, I can't do plasma physics. So I went to Jan Roy, who was the HOD. Yeah, I went to HOD office, and then I asked like, I don't want to do plasma. I want to do something else. And she said like, what else you want to do? I said like something in astronomy or something. So Dr. Swasati ma'am was there. Like she joined
Sure.
recently, and she told me like, oh, I can give you some. So I told him like, happily I will do. I'm very happy with that. I don't need something solid, just to. So she gave me a project in cosmology, and I had fun doing that. I really enjoy that. It was little different, and yeah, I had a good time with her doing that project, and I'm glad for her for giving me that project, because I didn't want to do plasma. Who do plasma now? Like even TV don't have plasma anymore. So I was like very unhappy about that project. So, but then when I got cosmology project, and then I started preparing for GATE, then I knew like, okay, now I have goal again, what I want to do. And by the end of preparation, even I planned, my plan B was like, if I don't get a good score in GATE, I will just take a break from science at for 1 year at least. I will go to uh, some place, like I will in KV and all. I can go and I apply for physics teacher bachelor's degree. I will teach them for 1 year, and yeah, that was my backup plan. Like taking 1 year of break and then starting refreshing. But gladly that didn't happen. Yeah.
So, what was your gate preparation strategy? Did you prepare like have to get under 100 rank, 100, 500 rank or something? And what did you study for
So
gates specifically?
so for gate, yeah. So Deepak Deepak Akre, I think you guys have known
Yeah,
him.
yeah, we have hosted
So
him
we
twice.
both were, okay, great.
He's now
Yeah. So I
okay.
sorry.
He was now posting videos flying planes in the United States.
Yeah, yeah.
Fun.
He loved playing so much.
Yeah.
Ah, okay. So we both planned like, okay, let's give get together. And that time we didn't have that much money, so we ordered some online material from Delhi. It's physics club or something. Get material. We both share money, and so if there are like two books, like there's a book on quantum mechanics, there's a classical mechanics. So if he's doing classical mechanics, I used to do quantum mechanics. So that's how we both prepared together actually. So we were sharing, we were talking. He was more serious than me, that's also true, because I had more like disturbing friend who was disturbing me a lot. But yeah, still, so for the whole preparation went like this only. I used to study in nights, and in daytime mostly sleeping only. But whenever we are, because I was not going to class, right? So nothing else is there. Either roam around with friend or prepare for gate. So for last 6 months, we both did that only. This
Right.
whole time if we are sitting, just preparing for gate, doing all the questions possible, reading materials, and doing some extra curricular activity if you want to do, but not. I didn't went to class. I remember that fourth year final exam, nanotechnology or something. When I went for exam, I didn't even knew that what the syllabus is. I just simply went because I never went to class, and I didn't. When I opened the book last night to prepare, I fall asleep, and then morning I just went and I wrote something. Somehow I got P, so I didn't fail. But
Okay.
that was my first worst marks in my whole career. But I have no regret for that because in nanotechnology I was not interested. So yeah, so we both prepare get together. We used to talk about it a lot. We used to discuss problem together. So yeah, he helped me and I helped him, I guess. So that's what a good time for us. So we both did it together. Yeah,
Right.
that's how we prepared. Like it took 6 months or something. At least once a day, just
Mm.
solve some question. If you are studying classical mechanics for too long, just change it, do something else. If you don't feel like solving problem at all, just read about some topic, uh, do something, and like this slowly, because honestly 6 months is more than enough to prepare gate, especially in physics, because there is not very high competition like at my time there was 12,000 application total was there, something like that. Yeah, so it's not very competitive, I will say. But yeah, but the
Right.
6 months is good to prepare for physics, math, and along with that, if you guys want more, mm, prepare for NET also. It's very important, and very, it's more difficult than GATE, but yeah, anybody can prepare. I didn't, but yeah, I was happy with the GATE only.
Right. So you got admitted to IIST. So what were the striking differences in terms of academics, specifically in IIST? And what's your review about the academics there?
Yeah, so it's quite different. First of all, so I got rejected from ISC Bangalore. Then I applied in ISC. In IST I applied in three subjects: astronomy, earth science, and geoinformatics. I gave the interview of astronomy and I felt happy. I thought like, okay, I did a good job and I will get the position. So I just left. I didn't even give the exam of interview for the two other subjects, art science and engineering. I just came back, and after a few days, I got the call later and I went there. It was a like there I felt like going to class studying because the teacher was very good. They were teaching very nicely. The talk was interesting, and like is they're not like just coming and taking notes and giving you notes. It was not like that. It's
It
like
was like
proper
a dream
teaching
come
only.
true. That is how classes should be.
Yeah, this is how classes should be. Their exam was not very tough. They were not worried about exam also. Okay, because they are teachers, so they will ask you to perform good. But overall, there was like just enjoy, study, and come to class regularly. And few of them was very cool. They didn't even care about coming to class. So I remember I in first semester of master I have a course in Python.
Hmm.
So before that I because NIT didn't taught me
Right.
computational physics very well, so I was very bad in that, and I was very scared like how will I study. But this professor, assistant professor Resmi, she was so good, she was so helpful. Just a minute. Yeah, so she taught very interestingly. She used to give us astronomical problem to solve with Python. Simple things. She never took exams. She never asked for interview. Oh, sorry, attendance. And even I remember the first semester exam I had. She gave us two questions, and she said like it's an open book, open internet. You bring your laptop. You bring whatever you book. just solve this problem and give it to me, and nobody was able to do it because it was a very difficult gamma ray radiation decay, some problem was there, and they asked me to solve the. But whatever we did, she was happy. She said like, okay, you guys tried. So it was like encouraging, right? You are not only just
Right.
reading from the book, you're learning something new also, and it was a very nice experience. And I studied a lot. I really enjoyed studying in IST masters, and I studied seriously for very after very long time. So there I used to go to class regularly, used to woke up early morning, which was very difficult for me, but I attended almost all the classes. I was performing very well in the subject also. So yeah, I was very happy there studying there.
True.
Yeah, I had a very good time. And then after 1 year, they gave us option also to which project you want to select. Not like IIS, NIT, just take this one. But they gave a list of project and associated professor's name, and they're like, you guys can select. So yeah, I selected the one because of which I am here right now. So yeah, I had a very nice time there studying. Yeah.
So, how did you transition from a master's student to this PhD program at Max Planck? Like, what was the sort of application process? How many interviews or exams, if anything, was needed? So, how was this PhD admission process, and what do you recommend to students who are planning to do a PhD in Europe?
Mm. Yeah. So after masters, I wanted to do PhD, and I wanted to do in India initially, but I didn't get any chance because but then in Max Planck I found a project which was very similar to my interest,
Mm.
which I did in master little bit and which I wanted to continue. So it's a very important point. Wherever you are applying, try to apply for the project which is like similar to your
Mm.
project, or like where you can use your experience to improve that project, right? So when you write in CV or in cover letter, you can put like this, like, oh, for last 6 months I was involved in this project, from this project I learned this, and this knowledge I can use to pursue my PhD. So it's a very important point. So try to find what you wanted to do or what you have experience in little bit. So yeah, so for after almost my masters happened, I applied for Max Planck. I applied only in two colleges
Mm.
outside of the India: Max Planck Institute for Radio Astronomy and Max Planck Institute for Astronomy. And I got selected for both of them for interview. So
Okay.
I gave interview here. So first time they asked me in the interview is to give a 10-minute talk, no, 12-minute talk on my project, master's project
Right.
in detail. And they said like, we want to listen to your project, and then we will ask question, and that's all. So another difference compared to when you apply in India,
Mm.
when you apply in India, they will start asking basic physics question. I don't think so they care about how much physics I know. All they care about like whether I am interested in doing this particular astronomy or not.
Research.
They care more about that than my knowledge. So like for in ISC Bangalore, they ask me question to solve the solve the Einstein field equation. How will I able to solve that? So they ask me this question in IISc Bangalore, and here nobody asks anything about the physics. They ask me to give a talk on your work,
Mm.
whichever you want to do, like whatever work you have done. Just give a 15-minute talk. We will ask question based on that, and I did that, and then went well. So I got a mail like, we liked your talk. We want to continue talking with you, but this time more informal. So I had another interview, informal interview. So that time they asked like, if we select you, what you want to do. Do you have any plan for your future, like this project I will be interested in, and if we provide you this data or this information, how you. So these type of question they ask, and it went nice only. So I answer whatever I wanted to do, and then they said, okay, we will get back to you. And was in 2020, and then COVID happened.
Right.
So everything was closed. So for 8 months I didn't had anything
Mm.
from neither from Max Planck Institute. So I was very tense that time. That was a very low point of my life because I didn't know what to do. So my professor in IIST, my supervisor, he gave me junior research fellowship. So during COVID, I was doing that only. Thanks to him, at least I had something to do, and I was earning also. Yeah. So after waiting for almost 1 year due to COVID, I finally got an acceptance letter from here, and yeah, it was a very, I was so happy, so relieved. And then after another 6 months because of COVID, I finally came here. And here it was very easy. I don't talk to random people like extreme very much. I'm not that a person, like kind of introvert or shy, you can say. Not extreme, but yeah, little bit you can say. But uh, even because of that, I didn't find any problem here. People are very nice to talk, then talk very nicely. There's no stress of work. If you want to do it. If you don't feel like, don't do it. It's up to you. So if like, it's like right now it's 5, so it's already office hour done. But if it's like 2 and I felt like, oh, I'm not feeling well, I can go home and sleep. I can do that. Nobody will ask question until unless you are doing something. Because we, after some
Right.
period of time, I have to show my supervisor like this. It's not like that I'm completely sleeping home for 3 years, did nothing, then it's a problem. But the point is like, there is no stress. There's no pressure from the higher authority, like do this, finish this in this time. Why you're not doing it? There's no such thing.
Right.
Even if I have some problem, I can tell them and they will understand it very nicely. So yeah, so I was completely okay. I didn't feel like cultural shock or anything. People say I didn't, because in India also I travel a lot, so I already had experience of cultural change. So I didn't find any problem settling here. Making new friend was difficult, obviously. It
Sure.
take time. I'm still trying to make friends, but it's difficult. Like, you're different country, different culture, your jokes are different from their jokes. Yeah, also all those things. But other than that, work wise is very nice. Like, you can happily do it. You can finish PhD here, go back to India for postdoc, or maybe postdoc here and then again go back to India. That's fine. Like, ultimately going to India will be like main goal. But yeah, it's very nice to
Yeah.
feel all this experience. So it's like, keep trying is a good thing.
So we have the
Mm.
final two questions. The second last question is this: that what is your opinion about research in Indian institutions right now? Because a lot of research has to take through a lot of paperwork, especially experimental work. So they have to write a lot of applications, then forward it to some office, then that will go to some another office. It will get sanctioned, and so on and so
Mm.
forth. So, what is your opinion about Indian research,
Yeah.
and what do you think can be done to improve it? What do you think about it?
Yeah. So first of all, the problem I find with this Indian research in recent time is innovation. So like, people are more worried about like publishing paper, finishing this that, so that they can show it to government or higher authority where funding is coming,
Right.
but not the innovation is coming. For example, if I see astronomy paper from India,
Hmm.
there are good paper, no doubt in that.
Sure.
It's, there are some institute doing very good job. Like, I will happy to go there and work. And like ISC, mm, Raman Research Institute, IST, TFR, those are very good,
Right.
but those are very high class college, right? Like 0.11% of all
India is that. Yeah.
India. Other than that, I feel like, yeah, people don't encourage your innovation. Like, if you want to do something new, something different, it's difficult for them to accept it or like help you in doing that. Yeah, that's one thing I will say. And funding wise, I yeah, funding is also difficult in India right now, but that makes sense also, because India is still in developing country, and like, we have much more things to do in the future. So we can't expect like funding like USA or Germany, and like that will be unfair. But yeah, but we are going in the correct direction. Hopefully things will change like in recent time.
Sure.
But right now funding is difficult, so that's why you have to build a community. Like, whenever you're doing research, the best thing is to do build a community, meet with different type of people, introduce yourself, so that in next time if you're doing something, if you want to do something, you can talk to them. And if they have money, and if they will be interested in your work, you will get funding time. So building a community is a very good thing, very important thing actually in research. um, because many of the institute has Indian institute like IST has a collaboration with Max Planck also, so they give them money to do research, uh, and vice versa. They give research also, like we are doing this that, that. So yeah, I really felt like and I didn't knew about that when I was in NIT, but I later realized building a community is a very helpful thing for the institute and for individual also, to meet new people, talk to them, share your interest, and be honest. Like you don't have to build up like, oh, I am interested in this that that. If you're not, then they will know they are doing this thing for like 40 years or something. They're very experienced people. You can't lie to so much experienced person. Be honest. And yeah, so keep trying, try for get internship and all. Those are also good thing.
Right.
I never apply for internship. I never got internship, but those are good. Those are good first step. And yeah, in India, it's always you can qualify an exam and start doing research. And in terms of experience, experimental physics, I have not much experience, like how the funding actually work for them. But yeah, but I guess you need some solid result to get funding, right? Like you need something to show that I won this much money because I did this in past, I will do it in the future. And to do in the beginning is the difficult part. If you don't have money, how will you do in the first place also to get the money in the second place? So there you need some this community and your collaborations per sort of thing, like can I do work for 1 month in your institute, can I join as an intern or just unpaid intern for 2 months in the summer vacation with you, and like those things. And if you are honest, if you really want to do something, and yeah, it, in India it will be little competitive, but hopefully if you do enough work and all. And even in foreign institute also you can do that intensive thing they do, so it's fine. Mm.
And finally, many of us who aspire to be scientists or want to do science or code engineering, at the cutting edge of research, we are listening to you today. So, um, in terms of a career or academic life, what do you want to advise these young students today?
So yeah, in terms of academic life, I will say if you are not interested, or if you have a doubt, then maybe going to PhD won't be a good option, because it's a time-taking process. You have to do lots of things without not getting much money, or it's take time like 3 4 years just to get one degree. And for 4 years you're continuously doing the same thing day and night. You won't, while sleeping you think about that, while walking. So unless you really want to do that, I will prefer to going job. And it's nothing bad in that. Yeah, it's also a good thing. People do that. People go to job for 2 3 months, 2 3 years, and then come back to academic. It's completely fine. uh, Doing job is also good option, completely option. And you can prepare for job also. Like people have done this. Mayank in our batch,
Right.
he took a job in IT. Now he's doing so well. So it's if you want to do that, if you have doubt, you can go for it. Like no need to, because you did BS in physics, so I have to do PhD. There's no such rule. You don't have to force yourself. Don't force yourself in anything. Just do what you feel like doing and what will give you happiness. Think about that. You guys have 4 year of time, so think about that. Take your time. No hurry. Like 4 year, you like most of them like sleeping only and doing something crazy only. But like take some time, alone time. Think what you really want to do. Can you do it? And if you can do it, how I will do it.
Right.
Talk to your senior or talk to the people who already did that, and get an idea and work on that. So these are the steps, and it can be anything. Again, I'm saying you don't have to do PhD. If you are in physics, you do whatever you want to do. If you like teaching, you go to some school and teach. It's okay. Like money is okay. Money is a problem, but you can somehow some manage. People manage that. But other than PhD, doing job, IT job, or any kind of job is good, very good, because in you can turn back to academic whenever you want in your life. And even in So in, for example, in Max Planck, they like people think about like, oh, this guy is doing PhD in Max Planck, oh, it must be so good. Yeah, it's good, but still I have seen many people leaving academics after doing PhD and doing just IT job. So it's fine, it's your life, you can change direction whenever you want, and the only thing you need is like you have to have a plan, what I will do, how will I do, and when I will do it.
Sure.
So take your time, think about your life, what you are doing, how you will do in future, and just go for it. It's fine. It's no pressure to just qualify those exams, no pressure to get a job and get a PhD in IIT or ISC or in some foreign institute. And if you really want that, you will get it. If you really want, you will get it if you have done a good job. If you are being honest to yourself, yeah, I really want that. It's not just to show off or just to convince yourself like, oh, I did this. It's not about that. Being honest to yourself and do little work. I'm not asking anybody to do very hard work, because even I have not done hard work in my life. I have not done that much hard work. But you should know what you want to do and do work on that, like little bit, small step at a time, but things will go. So yeah, so if anybody wants to do PhD, so I will say gate and NET, those exams. There are many exams actually. I
Right.
think JAM also is there. Prepare for that. And even you can start applying for masters in foreign, that's also fine.
Right.
You can directly come for masters and it's good. You will get especially in Europe, you will get even money for doing masters. So you can do that. So whatever you feel like doing it, do it. Job is fine if you want to earn more money, and you don't want to do the same thing for 3 years continuously, and it's very stressful job. It's you get stressed, sometimes very depressed. If think about, like, you are doing something for 6 months and suddenly you found out like what you are doing is wrong. So it's you will just your mind will like, okay, I'm done with my life, I don't want to do anything. So if you are ready for all those things, it's fine. And it's actually, it's part of life, it's fun also. I'm not discouraging to do PhD. I'm saying it's a part of life. Wherever you go, you will have to face all these things. Prepare yourself for all those things. So it's fun for me. Like, I am enjoying PhD so much. Like, it's
Right.
every day I have to learn something new. Sometimes if I don't, I just don't do it anything. So I'm not discouraging to do anything. All I'm saying, just decide what you want to do and work on that, and you will succeed. You will be happy in the end. Because this 4 year is for that only, to decide your future. Yeah.
Yeah. So with that, I think the takeaway message is to do what one he or she likes, and work hard in that
Yeah.
area. Maybe to enter the corporate workforce, or to get into research. And
Yeah.
the final idea is to build a career into that. So one has to work hard. Okay, thank you,
Yeah.
Vaya, for joining. I think it was a very
Thank you.
pleasant time listening to you. It was the first time that we are talking to someone from Max Planck from our institute. So it's like really nice occasion. And we
Yeah.
had your posters, around the campus. I will send you some of the images of that. So
Yeah.
yeah, it was really good to talk to you.